start recording this at this stage. Um, I wanted to go over the material that that's covered on exam 2 that we covered last week that I think is really kind of like basic to a lot of statistics that you're going to be working with in the future, particularly this idea of the difference between populations and samples. I'm going to start by just outlining those, some very basic description of the differences. Let's get rid of this. Okay, so we know that when we talk about populations, we're talking about the entire group of people, subjects, tests that might be involved. So this population is going to have a mean. If it's normally distributed, which generally we're trying to work with within statistics that we're working with normal distributions for the most part. It's normally distributed. It's a bell-shaped curve. It's symmetrical. The mean and the median are in the center. They're probably pretty close or the same, ideally, right? And we know from the empirical formula, the empirical rule, that within 2 standard deviations of the mean, we have 95% of the values and 99%, 99.97% within 3 standard deviations, and so on and so forth. Kind of went through that for the first couple of weeks in the first exam. So now we have more recently learned about the behavior of samples from a population. And we know that if we take repeated samples from this population and then we create a new distribution that's based on the sample means, repeated sample means from this population. Well, obviously, one of the things that we're interested in when we deal with samples is the sample size. Let's say, for argument's sake, sample size is 25. Repeatedly, randomly sampled people from this population, 25 at a time, found the mean, wrote that mean down, did it over and over again. We could establish a new distribution for the sample means. Okay, and what we would find is that sample mean distribution would have the same mean as the population mean, or to approximate the population mean, especially if we took many, many, many samples, right? Half the time it'd be less than the population mean, half the time more than the population mean. But it would be considerably narrower than the population. Why is that? Well, because if we're going to take sample size 25, we're not going to wind up with extreme values like we might in the actual population itself. Most of the values will be closer towards the center just because of averaging, right? And the relationship here is the mean it is approximated by the mean of the samples that we take, but the standard deviation, the spread of these two distributions are different. In one case, but they're related. In one case, we could call this sigma, right? The standard deviation and the mean we use Greek letters for the population. But for the sample distribution, the standard deviation of all the samples, that one is going to be much narrower. And the relationship is going to be standard deviation for all the samples, repeated samples, is going to be equal to sigma, the population standard deviation, divided by the square root of the sample size. The bigger the sample size is, the narrower, the smaller standard deviation, and the narrower is our sample size distribution. We give this standard deviation, we use the term standard deviation when we take a sample, but the standard deviation of the sample that we took, which approximates the standard deviation of the population. And we use X bar to represent the mean, which approximates the mean. So we need a special term to talk about the standard deviation of repeated samples and wind up with this narrow sample distribution, right? We're going to call that instead the standard error, SE for standard error. So the standard error, the standard deviation of repeated sample means, is equal to the standard deviation divided by the square root of the sample size. Okay, well, why is all this important? Well, it's important because now we have a certain understanding of samples and the nature of sampling that we can use to help us predict certain things. So, for instance, I'm going to open up. One of the things we can do with this is that since we know how samples behave, we can say to ourselves, Well, I'm going to take a sample, and let's say that sample X bar sample comes out to be equal to 100. Mean of the sample comes out to be equal to 100. Okay. Now, let's say the sample size here is very large. The sample size is I'm going to call it 100. Let's assume for a moment that that qualifies as very large. Okay. There's a lot of debate about what might be defined as a large sample that I don't want to really get into at this point. So let's say that when I take that sample, I also calculate the standard deviation in that sample, and it comes out to be, let's say, 20. Okay, well, when I look at this, I say to myself, well, this mean approximates the mean of the population. It's a big, nice big sample. Why wouldn't it be approximately the same as the sample of population? And this standard deviation approximates the standard deviation of the population. I'm going to make a big leap of faith here, and I'm going to say that forget about this. We know the population standard deviation. We got really lucky, and the standard deviation of the sample really equaled it, or someone told it what it was, or from some other previous big study, we happen to know what it is. If we know the population standard deviation, we completely understand how chance affects repeated samples of size 100 because we can now draw a distribution which represents repeated samples of size 100 where the standard error, okay, this might be what the mean is, right? The standard error is equal to standard deviation, which we say we know over the square root of the sample size, right, which is equal to 20 over the square root of 100, which is 10, which is equal to 2. So we know that if we happen to know the real population, then 95% of the samples would be between two standard deviations below the mean, two standard errors below the mean, and two standard errors above the mean. 95% of the samples that we would take from this population if mu was indeed equal to 100, right? If that was true, then 95% of the samples would be between two standard deviations above and below. In reality, we know that it's not really 2, that's an estimate. It's really 1.96 standard deviations below and above. Let me ask you, do you guys know why I use 1.96 instead of 2? Let's clear that up before I go any further, just so I want to make sure that we're all on the same page with that. Why would I use 1.96 instead of 2, which was the empirical formula? Right? I did that because really the real value for 95% of the population would be the range of z-scores that would only exclude 2.5% in the bottom tail and 2.5% in the top tail, leaving 95% of the population. Let me just show you that that's really true. I'm going to go to the z table, and I'm going to look up to see whether indeed, don't need that. I'm going to look up to see whether indeed a standard deviation of 2.0 represents 2.5% in the bottom tail and 2.5% in the top tail. Well, in fact, 2.00 represents 2.25% roughly, not 2.5%. Well, what would represent 2.5% of the distribution? Well, let's see. Where's 2.5% here? Well, right here. And what is that? That's 1.96, right? So a z-score of 1.96 or 1.9 standard deviations away from the mean is really what would represent 95% of the possible outcomes for these samples of size 100. What about if I wanted to know 99% of the possible outcomes? Well, 99% would represent 0.5% in each tail. And where would that be? And if I go over here, I see that the closest value that I get to that is going to be, let's see, 2.5% is going to be 0.5%, 0.05, 0.005. Where is it? It looks like it's around here. I'm going to use this one right here. 2.58 is the z-score that represents 99%. How about 90%? 90% would be 5% in either tail. So in the bottom tail, where would 5% be? That would 5% would be 1 point, let's try 6. 1.64 roughly estimates the 90% or 90%. A z-score of negative 1.64 to a negative z-score of plus 1.64 represents 90% of the possible outcomes that you would get for samples that you would take from this population that we know so much about. Well, the truth is, we very rarely know this kind of information about a population. All we really know is what we know from the sample. For the moment, I'm going to continue to make believe I know the population standard deviation, but I'm going to accept the fact I do not know what the mean is. I don't know what the point value is for the average for this entire population. That's never going to be, or very often we'll never know that. Just like we'll never know what the proportion is for an entire population. If I were to tell you we sampled 200, we randomly selected 200 people and 20 of them were diabetic, we know 10% of that sample was diabetic, but we don't know what the true p-value, true proportion for the entire population. That's also a point value that exists. It's a real number. We just don't know what it is. The only way we're going to find out anything about it is to estimate it by taking a sample. So let's look at the sample we just took. X bar is equal to 100. Our standard deviation is equal to 20. I'm going to write this down again. X bar equals 100. And we know the standard deviation is equal to 20. So I'm going to say to myself, well, gee, I'm going to start with this X bar is 100. I'm going to say to myself, let's assume that that is a good representation of the mean. I want to know how variable my samples might be, if my repeated samples might be. So I'm going to look for a range here. I'm going to say, let's start with that 100. And let's add and subtract the value that would represent 2 standard deviations to the left and 2 standard deviations to the right, or in other words, really 1.96. So plus or minus 1.96 standard deviations for the mean, the distribution of means, which is the standard error. Okay, I'm going to calculate that, but I'm going to call that something new. I'm going to call that a confidence interval. I'm going to call this the 95% confidence interval because that's where I would expect 95% of the outcomes to be. So what's that going to be now? That's going to be X bar. It's going to be 100 plus or minus 1.96 times the standard error. We already calculated the standard error is 20 divided by the square root of the sample size is 2. So basically, I'm going to round this off and call that 4. So basically, we're pretty confident that the true population mean, that most of these samples, or the true population mean, would lie between 100 minus 4, or 96, and 100 plus 4, or 104. Okay, well, we're going to use that a special way. We really can't use, since we don't know what the true mean is, we really can't predict what repeated samples might look like. We know that this does not represent the true mean because we just have to be extraordinarily lucky for that to happen. However, we do know that we would have expected that this sample would likely have come within 2 standard deviations of the mean. So the way we're going to use this confidence interval is we're going to say from now on, when we use this methodology, we're going to say we're 95% confident that the true mean, mu, is between 96 and 104. And what's our level of confidence? Our level of confidence is 95%. Okay, what does that mean? That means that if I did this 20 times, if I did this 100 times, I'm 95% sure that when I did it, that I would capture the true mean within my confidence interval. That means 95 times I would be right. I would capture it, but 5 times I would miss it and I would be wrong about it, right? But 95% of the time I would be right. Well, I can extend this even a little bit further. I can say to myself, let me take that same distribution. Mu is, X bar is equal to 150, right? Standard deviation, which I happen to know, normally I might not, is equal to 20. And my standard error, my sample size is equal to 100. So my standard error is equal to 20 over the square root of 100 is equal to 2, just as we saw before. Well, this time I want to know I want to know. I want to know. I want to be 99% certain that that I capture the true mean between the upper limit and the lower limit of my confidence interval. I want to make 99% sure that I don't miss the mean being between these two values. So let me ask you something. Would my confidence interval, I'm going to move this over just a little bit. I can see you can't see this control panel. It's kind of in my way a little bit. Okay, I am going to, let me go back here. I am going to recalculate my confidence interval, except this time, instead of being 95% confident, which gave me a confidence interval of 96 to 104 roughly, right? I rounded. Okay, I want to be 99% confident. Is my confidence interval, is these two numbers, are they going to be wider or is it going to be narrower? What do you guys think? Wider or narrower? Okay. Somebody take a guess for me. What do you think it's going to be, wider or narrower? Just think about it from, common sense perspective. If you wanted to be more confident, then be wider. Exactly right. Okay, you guys are shy, so I got a private message that said wider. But you don't have to be that shy, I don't think, right? Okay, we're all in the same boat here. But at any rate, it's wider. Makes sense, right? Because the wider you make your confidence interval, the more certain you are that you're going to capture the true mean for this population. In fact, we can actually go ahead and calculate that and see mathematically why that occurs as well. So now our confidence interval is going to be equal to, how are we going to calculate confidence? It's going to be X bar plus or minus a z-score, right? I'm going to use a z-score because I know the confidence and I know the standard deviation of the population. The appropriate z-score for the percentage that I'm looking at, the confidence interval that I'm looking at, times the standard error. Okay, so my mean is 150. That hasn't changed, or well, I guess it was 100 before. Excuse me. My mean is 100, right? Plus or minus. My standard error is the same as it was before, was 2 times, right, my z-score. Well, my z-score before was 1.96, which was appropriate for a 95% confidence interval. So what am I going to use for a 99% confidence interval? Anybody remember? Right? Remember we decided for 95% it was going to be 1.96. For 99%, it's going to be 2.58 is an appropriate z-score. And for 90%, it would be 1.64. Okay, so I would be using 2.58 here for a 99% confidence interval. Right? So let's take a look at that. That makes sense now, right? Because before it was 1.96. So now when I multiply the plus or minus, don't forget plus or minus. When I multiply 2.58 times 2, I'm going to get 5.16. Okay, that's 100 plus or minus 5.16. Okay, so now since I'm adding and subtracting this from this number, before I was adding and subtracting 4 so we can see that it's going to be wider. Since I'm adding and subtracting this from this number, I'm going to give this value, the z-score times my standard error. I'm going to give that value a special name. I'm going to call that the margin of error. Okay, and that makes kind of sense, margin of error. So I'm going to just round this to 5 and call it 95 to 105. And you understand it's going to be a little bit different. Really 105.16. And this is going to be 94.84, I guess. Right? So that is my 99% confidence interval. So I can also use this as a tool for calculating confidence intervals for proportions. But before I get to that, I want to discuss one other thing here. And that is that when we take a sample, start again, take a sample, and we find x bar is equal to 100, right? And if we don't know what sigma is, normally we don't know mu or sigma. Both of those are unknown to us. If instead we're forced, if I don't know sigma, where am I going to get my population standard deviation from? Well, I got to get it from my sample. So I'm going to call it SD or S and say my standard deviation from my sample was equal to 20 instead of my sigma is equal to 20. The problem here is that because I'm taking this from a sample, of size 100, and I don't know the population standard deviation, not only am I uncertain about my mean, now I'm uncertain about my distribution for my repeated samples. Okay, so I have an extra level of uncertainty. So I can no longer use 1.96, 2.58, and 1.64 for my various confidence intervals. Now I have to go to something that's a little bit more forgiving, and that is a t-distribution. If you play back the lecture, Levi's lecture, you will have gotten a lot of yeah, I kind of lost track there. Was it 150? Right? X bar is 150. It really doesn't matter. It really doesn't matter. We'll recalculate it. Yeah. Let's stick with that. Let's stick with that 150. I kind of lost track of it as I changed pages here. Okay, so this t distribution, our normal distribution, our standard normal distribution, may look something like this. Okay, and it's very predictable. We know that how this spread. We know that the z-scores here represent the various areas within this distribution. Now, when we look at our t distribution, well, what happens here, since we're less certain, our spread is wider for our distribution. Not only that, but when the t distribution is when the t distribution is done for a small sample, the spread is much wider. When the t distribution is taken for a slightly larger sample, it's narrower, and narrower again for a larger sample. When the t distribution represents the entire population or an infinite number of samples, well, then it actually matches an infinite sample size. Then it actually matches the z distribution. Z and the t distribution are the same. Well, what does that mean? That means since the distribution has a different shape, is wider, we need to use different numbers to represent the distribution based on the t distribution rather than the z distribution. And I'm going to pull up a table which is going to give us those numbers. Okay, let's see. Here we go, t table. Okay, let's take a look at this t table. In this t table, you'll notice that our 95% confidence interval, in other words, the percentage of outcomes that we would expect that would be within a tail, 2.5% tail at the bottom of the distribution and 2.5% tail at the top of the distribution. So 95% of the outcomes are between it, right? Well, when we look at that with this table, we see that if the sample size is infinite, then the t-score that represents the z-score or t-score that represents that spread is negative 1.96 standard deviations to the left and 1.96 standard deviations to the right. But as we get into smaller and smaller sample size, our t distribution is less certain, and the spread of the t-distribution is wider. So for a sample size of 10, right, we would be in this range, around here somewhere, in terms of what we should be using instead of 1.96. And we can see it's getting bigger and bigger and bigger the smaller the sample size is. And this accommodation will this will accommodate that extra level of uncertainty that you introduced by not knowing the true population standard deviation and being forced to use the sample standard deviation instead. Now, there's one other twist in here I got to tell you about, and that is, instead of using sample size, this table uses degrees of freedom. And degrees of freedom are basically represent the sample size minus 1 for our purposes here. So if we were looking at a sample size of 100, right, we would be up here, basically 199, probably be basically the same thing. So we would use the value 1.98 in place of the value 1.96. And to be honest with you, a lot of statisticians would say, well, since it's so close, why don't I just use 1.96, the z distribution? And that legitimately is the way a lot of people, a lot of statisticians might handle a situation where you have that big a sample size. So let's see how we would calculate our confidence interval here. So our confidence interval would be x bar plus or minus my t value for 0.025 in each side of the distribution, in other words, 5% or 95%, times my standard error. So it's 150 plus or minus our t-score, which is 1.98, times our standard error, which is still 20 divided by the square root of 100, which is 10, is equal to 2, times 2, right? So it'd just be a little bit different. Well, what about if our sample size was 25? Well, if our sample size is 25, well, the square root of 25 is 5, so our standard error is 4, but that's more complicated. Now we have a smaller sample size. So a degrees of freedom, sample size of 25, degrees of freedom 24, represents a t-score of 2.06. So instead of 1.96, we would use 2.0, I forgot already, 2.06 times, right, our standard error of 4. So now our 95% confidence interval, because of our smaller sample size and our larger value of t, is going to be 150 plus or minus 2.0 is going to be 8. It's going to be 8.24. Right? We add and subtract 8.24 and wind up with 141.76, comma 158.24. So now that would be our 95% confidence interval. So what about if I wanted a 99% confidence interval over a sample size of 25? Well, the t value I would use, again, 24 degrees of freedom, go across all the way to here. And if you notice, this last column on this table represents, up next to the last column on the table, represents the 99% confidence interval. 0.5% in the left tail, 0.5% in the right tail, leaving 99% in the middle. Okay, and for 24 degrees of freedom, that's going to be almost 2.8, basically 2.80, right? Where we would substitute 2.80 for this, and that would be 2.80 times 4, and added and subtracted to 150, and that would be our 99% confidence interval. Okay, so I'm going to do one more thing that involves this stuff, and that is this idea, what about a proportion? Okay, so I'm going to make up a problem that involves a proportion. Okay, let's say that there's a new bond bill being floated in New York State, and we go out and we poll 200 people, right? So our sample size is 200. Well, 200 people. Turns out that 110 people say that they're going to vote for this bill. Okay, so 110 people are going to vote for this bill out of 200 people that we polled. Now, that means that the percentage of people in our sample that are going to vote for this bill are going to be proportion is going to be equal to 0.55. 55% of the people are that we polled are in favor of this bill. Well, when we talk about proportions, a lot of times we reserve P to represent the population proportion, everybody that's going to vote for this bill, not just the 200 that we sampled. So to distinguish it, very often we use P cap to represent the sample proportion, rather than population proportion. So P cap is equal to 0.55. Well, just like before, the reason why we're so interested in the confidence interval is that when we know X bar for our sample is 150, just knowing that our sample mean is 150 doesn't help us very much because we don't have a context here. We don't know how close is that truly to the mean of the entire population because we don't care what X bar is. We're really interested in using X bar to deduce what mu is, what population mean is, right? Similarly with P, when we calculate P cap, it's 55%. We're not really interested in that. We really want to know how does that help me know what P is, the proportion for everybody that's going to vote on Tuesday. Okay, so really that's what we're after. Now, since we really can't get a handle on how close we are to the true mean, because we never know what the true mean is. However, by using the confidence interval now, instead of just looking at this as 150, now we can say that we believe that the true mean is between 145, I'm making these numbers up, 145 and 155, right? And I'm 95, I can quantify my level of certainty. I'm 95% sure that the true population mean is between these two. That's more powerful in a sense than just guessing at what the mean is from a sample. Because now, let's finish up this problem with the proportion. Okay, now I can do the same thing with proportions and say I want to figure out what's my confidence interval based on this information that I have here. Okay, so now it's a very large sample, right? So I'm gonna assume that we have a pretty good handle on what the proportion is. Okay, so these you can calculate the standard error for repeated samples for a proportion using this formula. I'm pretty sure it's in your on the formulas that we gave you in this segment. K is equal to the square root of p times 1 minus p over n. Okay, so what does that make our standard error? That makes our standard error equal to the square root of 0.55 times 0.45 over the sample size, which was 200. Okay, so let's actually calculate that out. The standard error, the variability or standard area for repeated samples of these from this population proportion, okay, is 0.55 times 0.45, 1 minus p, divided by 200, and then I'm going to find the square root of that. Okay, so it's 3.5%. So my standard error for this proportion is 0.035. Okay, well now let's use this to calculate a confidence interval. So now our estimate of the true proportion, our p cap, right, plus or minus some score, Z or T, times my standard error is going to give me my confidence interval. Well, since the sample size is very large, and in most cases, we're going to work with a very large sample size when we deal with proportions, like we're going to limit ourselves to large sample sizes. Okay, and for instance, we're going to make sure that either side of this is not less than 15 people, whether it's the yeses or the nos. In this case, we have 110 on one side, 90 on the other side, and our and our sample size overall is 200, so we're in pretty good shape. I'm going to go ahead and use the z-score for 95% confidence interval, 1.96. And most often you're going to be able to do that. If you can't, I'll give you a warning on a test or a homework. That might be an issue or something like that. Times the standard error. So what's our 95% confidence interval? Our 95% confidence interval for the true proportion for this population, the voting in this population, is going to be equal to 0.55 plus or minus 1.96 times my standard error. What was my standard error? It's equal to 0.035. Okay, I'm going to call that 7%, rounded off to 7%. So my confidence interval is going to be 55 plus or minus my margin of error, which is about 7%. So it's going to be 0.48, comma, 7%, going to be 0.62. I'm 95% sure that the true population proportion of people voting for this bond act or this proposal is between 48% and 62%. Well, let's think about what that means. If that's what our range for our 95% confidence for what we think the true population mean is, can I say that I'm 95% sure that this bill is going to pass, this bond is going to pass, right? What would it need to pass? What proportion would it need to pass? 50%, correct? Am I 95% sure that the true proportion is greater than 95%? Looks to me like I have to say no. Right, exactly. Looks to me like I have to say no because this overlaps 50%. Now, had our standard error, maybe it was a bigger sample, maybe different proportion, had our standard error been, somewhat different, like maybe 1%, right? In which case it'd be 2, and we wound up with a confidence interval of 0.53 and 0.57, right? Well, if I'm 95% certain the true proportion for the entire population is between those two, I'm also 95% positive that this proposition would pass. Similarly, we can do the same thing with the means that we were talking about before. We could look for whether or not the values that we want to compare it to are within that confidence interval or outside of that confidence interval, so we can say that they're different. A lot of times we're interested in proving things are different rather than the same, right? For instance, if we're testing a drug versus a placebo, well, we want to prove that the drug performs better than the placebo, not that the two of them are equal. If we want to prove that a intervention training, for instance, for training or drug intervention or something like that works, we want to prove that the group that didn't get the intervention is different than the group that did get the intervention. So we start off with them being equal, not being able to say that they're different, with the hope that we can soon say, based on evidence that we generate, that they are different. Okay, now that's where we transition now into this idea of hypothesis testing, and this is the tie-in to this, this idea of confidence intervals and using standard error and understanding samples and so on and so forth. This is where the real payoff is going to start to come from. Okay, so now let's talk about this now. Okay, so very frequently we are going to be in a situation where we might want to prove something like this, that two groups are different from one another, two means are different from one another. So I think I got a couple of examples here I can show you. Let me try to open them up. Okay, let me move this out of the way. Okay. Okay. Now, this first example here is what's called a single sample t-test. Okay, so I'm going to take a look at these numbers. My word is a little slow here. It takes a little while for it to catch up. And let me start scrolling or copying things from it. Hopefully it's not frozen. Ah, there it goes. Finally, it started to work. Okay. So I'm going to start with this sample. I took a small sample, single sample t-test, okay, with a known standard deviation of the population. Okay, so I'm going to take this and I'm going to say to myself, let's take these numbers and let's calculate what the mean, and we know the standard deviation from the population. Let's calculate what the mean is of these numbers. I think I actually have this as an Excel file. Okay, I believe it's the same file. Right? Looks the same. Okay, I'm going to assume it's the same. Okay, so let's take a look at what I can do with this. Okay, so I'm going to find the average for this sample of 9. Okay, the average is good. A little less than 10, 9.88. Okay, so now I'm going to take standard deviation. Well, I don't need the standard deviation because I know what sigma is. Okay, sigma is, let's see what sigma is. Sigma is 3, and my sample size is 9. Okay, so sigma is equal to 3, right? My sample size is 9. So my standard error is going to be equal to sigma divided by the square root of my sample size, or 1. 3 divided by 3 is going to be 1. Okay. So my standard error is equal to 1. So if I wanted to calculate a confidence interval, right, it's going to be equal to 9.8 plus or minus. Now I'm going to do minus first. Minus, actually what I'm going to do is I'm going to calculate my margin of error. Okay, I'm going to, just to simplify things. My margin of error is equal to my t-score times my standard error. Okay, so now my margin of error, my t-score, I don't need a t-score because I know the population standard deviation sigma. So I can use 1.96 even though it's a very small sample. 1.96 times my standard error, which is 1. So my margin of error is 1.96. So my confidence interval is equal to, the upper limit is going to be equal to this minus 1.96 times 1. 1.96. I'm sorry, I don't need to do that. I already did I already multiplied that out and got the confidence interval. Or it's equal to 9.8 plus, equal to 9.88 plus our margin of error. So our 95% confidence interval is 7.9 to 11.4. Okay, well, let's go back here and look at this problem. Okay, so I want to test to see if this mean, if this sample suggests that the population that this came from is different from another population that has a known mean of 8. Okay, since this is a known mean, it's a single sample t-test. I'm testing a sample of a population against a known value. A different population has a value of 8. So just looking at our confidence interval, would you say that you're 95% certain that this is different than this other population, which has a mean of 8? Probably would say not, right? Because it looks to me like it could be 8. That's where 8 is within our confidence interval, right? So it is within the realm of possibility that both of these samples, that both of these populations could have the same mean. The one that the sample was drawn from and this other population with a known mean of 8. Now, this is called a single sample t-test, because another way that I can use this is I can say to myself, well, my sample here, my X bar, right? My X bar is equal to 9.88. The value, my known value that I'm comparing it to, is equal to 8. Okay. Well, gee, that's interesting. Now let's think about this for a second. I know what sigma is equal to, right? So I know that standard deviation is 3. My standard error is equal to 1 because I was given that. I know that that's the truth. So I can say to myself, I'm working with a z-score, as I know. I used 1.96 before. Okay, let me see. The value that I have for x bar, that value is equal to 9.88. How far apart are these two values? Well, these two values are, let's see, this minus this. These two values are 1.88 apart. How many standard errors apart are they? Well, standard error is equal to 1. They are, okay, well, how would I calculate that? Remember how we found the z-score? We said the z-score is equal to the value you're checking minus the mean you're comparing it to, over the standard deviation, right? Well, we have all that. We have the difference, x minus mu, right? Divided by sigma. Sigma happens that sigma, excuse me, sigma, but sigma in this case is our standard error because we're dealing with a sample. So that would be for a population. So our value for z, for the number of standard deviations apart, I'm using z instead of t here because I know what sigma is. Our value for the number of standard deviations that these are apart is equal to this minus this divided by 1. In other words, 1.88 divided by our standard error equals, so it's going to be equal to this. So these two things are 1.88 standard deviations apart. Okay, let's go to our z table. Okay, our z table, let me find it here again. There it is. Nope, that's not it. There it is. Okay, our z table, I'm going to look for a z-score of 1.88. 1.8, 1.8, 0, 1, 2, 3, 4, 5, 6, 7, 8 is 0.03, is 3%, right? So that means that these things are far enough apart that I would likely get a value that's further apart 3% of the time on the low side. But remember, it's symmetrical. Same thing's going to happen on the other side, 3% on the upper side. So I would get this extreme of difference between those two means 6% of the time if there were no difference between the two population means. It would only come up 6% of the times that big a difference. Well, you know something, 6% is a chance of being wrong if they say they're different. 6%, gee, that's like a 94% confidence interval. So I'm not happy with that. I want to be 95% certain. Another way of saying that you're 95% certain is to say that you're less than that you're less than 5% chance that you would be wrong in saying you only want to accept this if you say that there's 5% chance that you would be wrong if you said that these two means were different. Okay, so I want to be 95% certain before I say that. Or in other words, I want to have less than 5% chance of being wrong. Well, in order to have less than 5% chance of being wrong, instead of Z being 1.88, you would need Z to be at least 1.96 or larger because you know that's what represents that difference. No, we're dealing with the standard error here. Three represents the standard deviation of the population. We're looking at standard error here because we're using this to represent a sample means, or distribution of sample means. Just like we use standard error when we were working with confidence intervals, when we're looking at the difference between two means, we're going to use standard error as well because they both, or at least one of the two of them, and very often both of them represent samples rather than the actual population mean. Okay, so at any rate, so we want less than 5% chance of being wrong if we reject the null hypothesis. Well, now let's think about what we're doing here. Okay, so in this case, these two values are not far enough apart for me to be 95% certain that the two means are different, or to be less than 5%, or for me to be satisfied that there's less than 5% chance of my being wrong if I say that they're different. Okay. Well, now we're going to look at this from another perspective, and that is, I am going to, let's see, where's my, there it is down there. I'm going to introduce a new concept here. I'm going to say to myself, let's formulate, let's describe or formulate. I'm having a problem here with this. My tablet here. Up here we go. Helps if I point this the right direction. There we go. Okay. I'm going to take a look at this from another perspective. I'm going to say to myself, let's create a new way of describing this process. And what I'm going to call that is hypothesis testing. I'm going to start out with the idea that there's no difference between these two means. In other words, the mean for group 1 is equal to the mean for group 2. Okay, that's my starting point. Since that's my starting point, I'm going to call that hypothesis my null hypothesis. Right? That's my starting point or my basis hypothesis. Sometimes you'll also see H with something like that through it for null hypothesis. Okay, that's my null hypothesis. So I'm going to say that's my starting point, but what I really want to prove is an alternative hypothesis. And the alternative hypothesis is that the two means are different from one another. Okay, so how am I going to do that? Well, the way I'm going to do that is by demonstrating that there's less than 5% chance that I'm wrong by rejecting the null hypothesis and accepting the alternative hypothesis. In other words, I want 5%, less than 5% chance or 95% certainty that I can reject this null hypothesis and then say that I accept the alternative instead. Okay. Notice that I say reject the null hypothesis, assuming that we prove there's less than 5% chance of them not being different, and then accept the alternative hypothesis. How are we going to do this? Well, we're going to calculate a probability of being wrong. Well, just before we found that the z-score for the difference between the two sample means, or the sample mean and the known mean that I had before, it was a kind of a combination, right? It was a one sample t-test, one sample test. Lost my pen again. Oh, why am I not writing? Oh, you hang loose. Come on. Hang on a moment while I get this working again. There we go. Okay. So when I looked at this before, my z-score was equal to 1.88. And when I looked it up on my table, well, that came out to a probability of having this extreme of difference, which was equal to 2 times 3%. In other words, we could get this extreme of difference between the mean and the value I compared it to 6% of the time. Well, I needed to be less than 5% in order to say that they're not the same. I have a 6% chance that I'm wrong, that they really are the same, and they're from the same population. Those two means are those two means that I'm comparing. So I need that to be less than 5%. Right now, my p-value, my probability of being wrong, is equal to 6%. I get my p-value by looking up the z-score and the area that it represents in both the lower tail and the upper tail added together. Okay, less than 6% or less than or equal to 5. Less than 5%, I would say. Less than or equal to 5%. Everybody asks me about whether, every semester somebody asks me, well, what if it's exactly 5%? Well, I think in most cases you would just reject the null hypothesis. You'd be so happy that you got that close, you'd reject this null hypothesis. Okay, so this test was rather unique for two reasons. One reason is because I told you that I knew what sigma was. I keep disabling this pen. Accidentally. Let me try this again. Okay. First thing I told you is that I knew what sigma was, right? Most of the time I won't know that. And this was also a one sample t-test. We're only dealing with a single sample, not two samples. Okay, so now, how am I going to apply this to more complex situations? Well, the way that we're going to do this, number one, is I'm going to take another look at this problem, except this time I'm going to say to myself, what if I didn't know what sigma was? Where'd it go? Okay, let's see if I can't find that paper again. Uh, okay. Okay, single sample t-test, unknown sigma, right? Well, this gets even a little bit more complicated, doesn't it? It's the same thing. My standard deviation here, what did it come out to? I'm going to go back to my Excel file. My standard deviation was sigma. Well, actually, I got to calculate my standard deviation now. Now, it's not going to be sigma anymore. It's going to be the standard deviation, right? What's the standard deviation equal to? It's equal to the standard deviation of this group, of this sample. That's going to approximate my population standard deviation, and it's 2.93, right? So now 2.93 is my standard deviation, okay? And my sample size is 9. My standard error is going to be, I'm going to use this in place of sigma, is going to be 0.978. And my margin of error is going to be equal to 1.96 times my standard error. Oops, wait a second. That's not true, is it? My margin of error, I can't use 1.96 anymore because I don't know what sigma is. I have to use the t-value that goes along with a sample size of 9. Let's take a look at that, a 5% chance. Let's take a look at what that might be. Here we go. There's my t-tests. Okay, so sample size of 9 is 8 degrees of freedom. And for 95% confidence or 2.5% in each tail, in other words, alpha equals 5%, 8 would be our degrees of freedom. And the t-score that we would use is 2.3. So now, instead of using, let me get back to, so instead of using 1.96, I would have to use 2 point, and I forgot the damn number already. It's hell getting old. Let's see, 2.306. 2.3, I'm trying to rush because I know I'm keeping you guys up late tonight. 3.06, I'll call it 2.31, right? Times that. Now my confidence interval now became wider because of that extra uncertainty introduced by that t-value. And in fact, now if I go down here and I actually calculate this again, my standard error, okay, is equal to uh, where am I now? I forgot where I was. Okay, is equal to 9 point. Let's my confidence interval is 7.62 to 12.1. It automatically updated because my margin of error was a bit larger. Well, what about my t-score? The difference between these two values. That's going to represent a t-score now, not a z-score. So the mean that of my sample group is 9.88. The mean that I'm comparing it to is 8. The difference is equal to 9.88 minus 8 divided by my standard error. Okay, my standard error now is, where's my standard error? Is that. So my t-score is 1.93, right? Well, the only problem now is that now instead of comparing this to 1.96, I got a little bit of a problem here. I don't know sigma. I can't use a z-score to compare it to. I have to compare it. Is that a big enough t-value? That's a t-value now, not a z-value, because I don't know my population sigma, right? Is that t-value big enough to represent a 95% confidence that these two are different? Less than 5% chance that those two are different. I'll give you a hint ahead of time. It's not going to be, right? Because we can see it's less than 1.96, and my t-value now is going to have to be bigger than 1.96 in order to reject this null hypothesis and say the two groups are different. So I'm going to go over here and I'm going to take a look at that confidence interval, my t-values. And for a sample size of 9, 8 degrees of freedom, I would need a t-score, a difference between the two values divided by the standard error. I would need a t-score that's bigger than 2.3 in order to be able to be sure that I'm 95% confident that these two means are different. Now, I don't know what the p-value is here. I'll show you how you might be able to calculate it. But this t-value, this value right here, 2.3, is what we call the critical value of t. The value of t I need to exceed in order to reject my null hypothesis that the two means are really the same. Okay, so I failed to reject my null hypothesis again because this needed to be greater than 2.3. Okay, now I could actually do this in SPSS. In fact, I have a file which represents this in SPSS. Let me open it up. Boy, I am keeping you guys up late. Oh, I don't want to do that. Open, data, and I'm going to navigate to desktop. And let's see. I think I'm in here. And I think I'm in here. And here we go. Single sample. It's the same numbers, I believe. Okay, same numbers that we were working with before, except now they're numerical variables, just called x for expediency's sake. Okay, I'm going to go in here. I'm going to go to analyze. I'm going to ask it to analyze. I could ask it to analyze descriptive statistics, and it would, or explore, and it would give me the mean and the confidence interval and so on and so forth. Right? Let's do that. What the hell? Okay, statistics. It's going to give us a 95%. We get ask it to give us 99% by changing that number. I'm going to click OK. That's really all I want for now. And let's see what it tells me. The mean is 9.89. We got that, but we got 9.8888, whatever, right? And there's our standard error, same as we calculated. There's our confidence interval, same as we calculated it. Okay, and now I'm going to ask it to compare these two means, right? And I'm going to go get this out of the way, go back here. I'm going to say analyze. This time I'm going to say compare means. When we go to compare means, it gives me access to one sample t-tests, independent sample t-tests. In other words, two groups independent of each other. Paired sample t-tests, right? That's a special kind of t-test that we'll discuss shortly. Okay, maybe not tonight, but what we did now was a one sample t-test. Okay, well, how am I going to do this? Well, one sample t-test, I'm going to move the test variable in there. That's my sample. Well, the test value is the mean that I'm comparing it to. The number I'm comparing it to happened to be 8. Okay, and I'm going to say, okay, go ahead and do that t-test. And it actually does the test we just did, the math we just did. And it says, you know, the difference between these two, the t-value difference between these two is 1.931. What did we say the critical value was that we need to exceed in order to get a p-value less than 0.05? Well, that critical value was 2.3. So we know we're not going to get a probability of being wrong that's less than 5%. So if I go over here, it actually calculates the value. When we used the table, we could only know whether or not we exceeded the critical value that we needed to in order to reject the null hypothesis, say that they're different. But when SPSS does the calculation, it actually calculates a probability for us. It calls it the significance. And the probability that we would be wrong if we reject the null hypothesis and say that these are different is 9%, is greater than 5%, so we fail to reject the null hypothesis. Had this been 4%, we would have gone ahead and rejected the null hypothesis. That would have only happened if the t-score was greater than 2.3. Okay, in this case, for this sample size. Okay, now let's take a look at another situation here. And these other situations are situations where, for instance, I have two samples, two separate independent samples, and I want to compare the means of the two samples. I'm just going to show you what it looks like in Excel, but I'm going to do it in SPSS. Okay, so two sample t-tests. Here's what it looks like in Excel. Here are two groups, male and female. These are the values that we calculate for each one of them. And the males and females, we're going to calculate a mean for each sample, a mean for this sample, a mean for this sample. And then we want to compare the two means. And the way we're going to do that is we're going to take mean 1, x bar 1 minus x bar 2, put it over the standard error to see how many standard deviations apart that they are. A little complication here. If this has a certain standard deviation and this has a certain standard deviation, which one of the two standard deviations should we use? Well, in fact, that actually is a complication. We could actually pool all the values and just calculate a single standard deviation, a pooled standard deviation. We could actually individually use these two separate standard deviations. So we have a lot of choices there. But our null hypothesis is the mean for males is equal to the mean for females. Our alternative hypothesis is that the mean for males does not equal the mean for females. So I'm going to solve this problem using SPSS. But before I do that, I'm going to show you the formulas that are involved when you consider all these different kinds of t-tests. Okay, so let me make sure I'm at the top here. So when we compare the means of two populations, okay, using the t-test, right, there's one situation where when you have a single sample t-test, you don't have to worry about that. You only have one standard deviation because you don't know what standard deviation for the other sample. Only one sample. Standard deviations, if we assume that the standard deviations of the two groups are equal, we use this formula to calculate a pooled standard deviation. Then we plug it into this formula, and this represents our standard error. So we look at the difference between the two means divided by the standard error, just complicated by this formula, and we calculate what the t-value is. The degrees of freedom that we use to determine what's our critical value at t is the sample size for group 1, sample size for group 2, minus 2. So for 9 and 9, it would be 18 minus 2 would be 16. The sample size is 16, 15 degrees of freedom. And we would find our critical value at t and see if we exceeded that critical value of t. Alternatively, we could do this in SPSS and actually calculate a p-value. This is the formula that we would use if the standard deviations are assumed not to be equal. Well, when might you assume that they're not equal? You might assume that they're not equal if the standard deviation of one group is, say, twice the standard deviation of the other group. If they're within twice of, if each one of them is not twice the other, but if within that range, we probably would use the pooled standard deviation. But if they're more than twice, if one is more than twice the other or less than half the other, then we would probably not assume them to be equal and use this formula for the t-value, x bar minus x bar 1. And for standard error, use the standard deviation squared for each of the two groups over the sample size of the groups added together to find the square root. And then the complicated part would be calculating degrees of freedom. This is such a complicated formula that most people would just say, I'm going to take the smaller of the two groups and subtract 1 and use that as the degrees of freedom just to be ultra conservative. I actually described there what you might do there. So, and when we're working with proportions, we probably would do the same thing and calculate a pooled standard deviation. And here's the formula for calculating, except we would use the z-score at 1.96 instead of using the t-score, because we always work with large samples when we're working with proportions. So let me just go to SPSS and show you a two-sample t-test. Analyze, compare means, independent samples t-test. Okay, I have to open a new file. New, open data, and here we go. What a surprise! Two-sample t-test. Okay, and here's our two groups. Okay, now notice that you have to organize it a bit differently in SPSS. Gender is assigned the number 1 and 2, values 1 and 2. So for each subject, have a value and a gender, sub-value and a gender value. It's not going to be in two separate columns the way it was in Excel. It just formats differently in SPSS. So let me go ahead and actually analyze this. Analyze, compare the means of these two groups, independent samples t-test. Okay, what are the values? The values are the actual numbers, and the grouping variable is gender. Now it's going to ask me to define the groups, and they were 1 and 2, represents the two groups, male and female. You have to tell SPSS about that. And I'm going to go ahead and make sure it's 95% coverage. Okay. I'm going to go ahead and click OK. And it's going to split these up into two groups, right? And it's going to actually calculate the difference between the two means, that mean minus this mean, divided by the standard error. Notice there's two standard errors, one for this group, one for that group. We have to decide, SPSS has to decide which one to use. Should I use it? Should it pool it? Should I calculate it individually like you saw before? Well, the way it figures that out is these 4 boxes here underneath Levine's test for the equality of variances. You always start with a null hypothesis where the variances, everything starts as a null hypothesis, including this. Levine's test for equality of variances starts with the assumption that the two variances, the 9.9 and 6.48, are equal, are not different enough to say that they're different. Or in other words, another way of saying equal. Okay, so SPSS does a test for the equality of the variances, and it calculates this value here, F. And it calculates a probability, a p-value, a significance to go along with that, which is 0.245. Well, what kind of significance do we typically want in order to reject the null hypothesis? Less than 5%. So this isn't enough to reject the idea that these variances are equal or could be equal. So that means that we would use the top row here for our t-value calculations, rather than the bottom row where we would have rejected equal variances and said they're not assumed, and use the bottom row if that had been less than 0.05. So we're going to use the top row. Notice there's not that much difference anyway. So the t-value is 2.184, 16 degrees of freedom. Remember 18 minus 2. And the significance comes out to be 0.44. In other words, the probability of being wrong if we reject the null hypothesis is 0.044. Should we reject the null hypothesis? What do you think? What do you think? Should we reject the null hypothesis here? Yes, because the probability of being wrong is less than 5%, and we can go ahead and reject the null hypothesis. Okay, one other thing we might do, you can say analyze, open. I just want to show you one more thing here. Open data, and let's see, paired samples. In paired samples, we have another situation here. We have each subject spent a few weeks taking a placebo and a few weeks taking a drug. So they have values. This person was 7 and 5 and 8 and 4. So it's the same person using the same person that was both in the placebo group and the drug group, the test group, right? And so we're not really interested in the actual value. What's more interesting to us is the difference. Which was did this person 6 and let's see, this person didn't get the difference between placebo group and the drug group for this person was 0. So we could just calculate a 0 here. For this one it was 7 and 5, so the difference was 2. 8 and 4, difference was 4. This one was 9 and 12, so it was minus 3. So we could actually just analyze all the differences and see if the average difference is different than 0 when we deal with paired samples like this. And in fact, if I go ahead and do that, analyze, compare means, paired samples t-test, and I tell it, okay, here's the pair, placebo and drug. Okay, and then go ahead and make sure it's 95%. Okay, then go ahead and say, okay, it'll do a t-test comparing the average difference between each individual subject, the average difference between each individual subject with the value 0. And it does it, finds the mean difference is 1.55. So is that different enough from 0? Standard deviation 2.64, the standard error is 0.89, and the t-score is 1.730. Does that sound like a t-score that would allow you with a small sample like this to reject the null hypothesis? No, right? It should be pretty big, shouldn't it? Okay, well, let's look at what the significance is. Significance of the p-value, probability of being wrong if we reject the null hypothesis is 0.12, 12%. We need that to be less than 5%. So we fail to reject the null hypothesis that there is a difference between these two groups. How do we find pooled standard deviation using SPSS? Well, it calculates it for you. Okay, it actually, if you look back at the independent samples t-test, this, if it assumed equal variances, then it based this on finding the pooled standard deviation. If it didn't, then if this was less than 0.05, it would not have used equal variances. It would have used the other formula, unequal variances, and calculated that. And remember that complicated formula for degrees of freedom where I just said, ah, the hell with this, just take the smaller number and subtract, smaller sample size and subtract 1. Right? Well, it actually calculates it. That's why it gets just such a bizarre number for the number of degrees of freedom. So you can see that it used that formula to actually calculate this stuff. Okay, so we went about 90%, about 50% over the time I was hoping to spend on this tonight. But I'll tell you what, if you email me or put on the discussion group some additional questions, I'll try and post some more discussion on this stuff. I wish that this semester had another 10 weeks left to it. But man, it's just, you guys have real. I have to tell you that I appreciate the effort that you've put in to doing keeping up with the homeworks and the first test, and now this test, and so on and so forth, and just just staying with the course, because it's just such a sprint. Okay, I hope so. I hope it is. I wish I just had more contact with you guys and more time with this stuff. But yeah. All right. Okay, guys. Have a good night. Do your best on the exam. There were some adjustments I would have made to the exam, but somehow or other, for some reason, the version that I have of the exam doesn't exactly match the corrections I made that appear on your version. And I'm afraid to play with it for fear that I'll really mess the thing up. So if there's any questions that if there's one question at least that I don't think makes any sense, I will make sure that I accommodate for that and everybody gets the points that are available for that. So good night. I'll get this converted as quick as I can and post it again. So take care, and we'll move on pretty quickly to this next part with chi-square and odds ratio and analysis of variance, which is pretty interesting stuff. And not real complicated calculations. Use SPSS quite a bit for those things as well. So on a realistic basis. So let's get past this exam. Then I'll post the next one, and we're really almost done. So take care, guys. Bye.